the atomic bomb almost failed because its explosives wouldn't explode correctly. That sounds impossible. Explosives are supposed to be the easiest part of a bomb. But in 1945, power wasn't the problem. Control was. The device that ended World War II required 32 separate explosive charges to fire at nearly the same instant within a few millionths of a second and push inward instead of outward. If even one charge fired slightly early, slightly late, or in the wrong direction, the weapon wouldn't detonate properly. It would tear itself apart before the nuclear reaction could begin. Most scientists believed this idea couldn't work. Some said it went against the basic behavior of explosives. Yet everything depended on forcing chaos to behave with precision just long enough to change history. For most of the Manhattan Project, the bomb seemed almost straightforward, at least in theory. Take enough nuclear material, bring it together fast enough, and a chain reaction would do the rest. That was the logic behind the original weapon design, the gun-type bomb. 2 subcritical pieces of uranium would be fired together using conventional explosives. Once they formed a single critical mass, nuclear fission would begin, releasing an enormous amount of energy. Simple, elegant, reliable. By 1944, this design worked perfectly for uranium-235. But uranium was rare, painfully rare. The enrichment facilities at Oak Ridge were operating around the clock, yet they were producing usable material at a glacial pace. Every additional bomb would take months. If the war dragged on, there might not be enough uranium to matter. That's why plutonium was supposed to be the solution. Plutonium could be produced in reactors, not painstakingly separated from ore. In theory, it meant faster production and more bombs. And for a brief moment, it looked like the Manhattan Project had solved its biggest bottleneck. Then the test results came back. In April 1944, physicist Emilio Segre and his team examined the first reactor-produced plutonium samples from Hanford. What they found was devastating. Reactor-bred plutonium wasn't pure plutonium-239. It contained plutonium-240, an isotope with a much higher rate of spontaneous fission. That detail changed everything. In a gun-type bomb, the 2 pieces of nuclear material take a small but critical amount of time to come together. With plutonium-240 present, the material would begin fissioning too early. The chain reaction would start before full assembly. Instead of a nuclear explosion, the bomb would blow itself apart. Not with a devastating blast, but with a weak, useless fizzle. The most powerful weapon ever conceived would fail before it even formed. When J. Robert Oppenheimer learned this, he faced an impossible decision. They could abandon plutonium entirely and bet the war on uranium-235, despite knowing there wasn't enough of it. Or they could attempt a radically different approach. One that most physicists believed bordered on fantasy. Implosion. The idea sounded simple only until you thought about it. Instead of firing 2 pieces together, implosion required surrounding a subcritical sphere of plutonium with high explosives and detonating them simultaneously. The shockwaves would rush inward, compressing the plutonium to a higher density enough to achieve criticality in a fraction of a microsecond. On paper, it worked. In reality, it contradicted everything explosives were known to do. Explosives don't converge, they diverge. They spread energy outward, shattering objects in all directions. Asking them to collapse inward evenly without tearing the core apart seemed absurd. Many scientists believed the problem wasn't just difficult. They believed it was unsolvable. Even those willing to try had no idea how to begin. Early experiments were crude. Cylinders wrapped in explosives emerged, twisted and uneven, crushed like empty cans. Nothing remotely resembled the perfect spherical compression required. Yet there was no alternative. Plutonium had already been produced. Factories were running. The war clock was ticking. Implosion wasn't a clever option. It was the only option left. And to make it work, the Manhattan Project would have to do something no one had ever done before: force explosives to behave with precision instead of violence. That realization marked the moment when the project quietly shifted from nuclear physics to something far more dangerous. A completely new kind of engineering problem. Implosion sounded elegant in theory. In practice, it was a nightmare. The moment the Manhattan Project committed to implosion, they entered territory no one had ever mapped before. There were no manuals, no proven equations. No weapons program in history had ever attempted to make explosives behave this way. Early tests were brutally honest. Engineers wrapped metal cylinders in high explosives and detonated them, hoping to see uniform inward compression. Instead, the results were chaotic. The cylinders emerged twisted, flattened, and asymmetrical, crushed like empty cans stepped on from one side. Nothing collapsed evenly. Nothing compressed cleanly. Shockwaves raced through the material at different speeds, colliding unpredictably. Some sections moved inward faster than others. Some rebounded outward. The shapes left behind looked less like engineered devices and more like industrial accidents. For a nuclear weapon, that kind of asymmetry was fatal. To achieve criticality, the plutonium core needed to be compressed evenly from all directions at nearly the same instant. Any distortion, any uneven pressure would cause the core to squirt out sideways, relieving pressure before the chain reaction could build. In other words, the bomb would tear itself apart before it could explode. At this stage, many physicists quietly concluded what they had suspected all along. Implosion wasn't just difficult. It was fundamentally wrong. Explosives, by their nature, expand. They release energy outward in all directions. Asking them to converge inward violated the most basic intuition about how detonations worked. Some scientists argued that even if implosion could be made to work in small experiments, scaling it to a full weapon would introduce uncontrollable errors. The more powerful the explosion, the worse the asymmetry would become. Meanwhile, time was running out. By mid-1944, plutonium production was already underway. Reactors were running. Material was accumulating. Every month that passed without a viable weapon design meant stockpiles of unusable plutonium and a project drifting closer to failure. The pressure inside Los Alamos intensified. Meetings grew tense. Progress reports became uncomfortable. The implosion group struggled to show convincing results. Each test consumed scarce explosives and produced more discouraging data. One physicist, who had been advocating implosion since early 1943, found himself increasingly sidelined. His experiments had proven the problem existed but not how to solve it. Leadership began to lose confidence. What the project needed wasn't another incremental test. It needed a completely different way of thinking. The breakthrough didn't come from trying to make a single explosion behave better. It came from questioning a deeper assumption, that an explosion had to be uniform from the start. Instead of asking how to make one explosive converge, a radical question emerged. What if convergence could be engineered? What if shockwaves could be shaped? At first, the idea sounded absurd. Explosives weren't light. Shockwaves weren't flexible. But a few people began drawing analogies anyway quietly, almost apologetically. Light behaves differently when it passes through different materials. Glass bends light, focusing it into a point. That's what a lens does. Shockwaves also change speed when they pass through different materials. If a shockwave traveling through a fast explosive suddenly entered a slower one at the right angle, it wouldn't continue straight. It would bend. The implications were staggering. Instead of detonating a uniform shell, what if the weapon used multiple explosive blocks, each precisely shaped, designed to redirect shockwaves inward? Not one explosion. Many explosions, carefully sculpted. The idea of an explosive lens was born. But ideas were cheap. Reality was not. Even if explosive lenses could work mathematically, they introduced an entirely new set of problems. First, no one had ever designed explosives with this level of geometric precision. Traditional military explosives were cast, packed, or molded with tolerances measured in centimeters. This concept required precision measured in thousandths of an inch. Second, the materials didn't exist. To bend a shockwave, the system needed at least two explosives with very different detonation speeds, one fast, one slow. And both had to be castable, capable of being melted and poured into molds without degrading their explosive properties. In 1944, the United States did not possess such materials in usable quantities. Common explosives like TNT were reliable and stable, but too slow. Faster explosives existed in laboratories, but they were unstable, difficult to manufacture, or impossible to cast precisely. Even worse, combining explosives introduced new dangers. Different detonation velocities meant different pressures at boundaries. Cracks, air pockets, or contamination could ruin the entire effect or cause a premature detonation during manufacturing. At this point, the implosion problem had quietly transformed. It was no longer just a physics problem. It was a chemistry problem, a manufacturing problem, a logistics problem, and none of them had easy answers. As the months passed, frustration mounted. Engineers tried refining earlier tests. Mathematicians produced increasingly complex equations. Experimental data piled up, often contradicting predictions. The implosion group faced a dangerous perception. They weren't just failing, they were consuming time and resources while offering no guarantee of success. Some began to question whether the project should cut its losses. But abandoning implosion meant abandoning plutonium. And abandoning plutonium meant betting the war on a single uranium bomb, assuming it could even be completed in time. The stakes couldn't have been higher. The atmosphere inside Los Alamos shifted from optimism to urgency. This was no longer a question of elegance or theoretical purity. It was a question of survival for the entire program. If implosion failed, the Manhattan Project might still exist on paper, but its most ambitious promise would collapse with it. What finally broke the deadlock wasn't another failed test. It was the arrival of people who approached the problem without loyalty to the old assumptions. They didn't ask how explosives had always behaved. They asked how explosives could be forced to behave if everything about their shape, speed, and timing was controlled. To make implosion work, the project would have to abandon traditional explosive science entirely. It would have to invent a new field: precision explosives. And that realization marked the end of the dead ends and the beginning of something far more dangerous. If implosion was going to work, the Manhattan Project had to stop thinking about explosions as single events. That assumption that an explosion was one violent moment spreading outward had quietly sabotaged every early test. The failures weren't random. They were consistent. Every time the team detonated a uniform shell of explosives, the shockwave behaved exactly as physics said it would. It raced outward, reflected unpredictably, and crushed the metal unevenly. The problem wasn't execution. It was the idea itself. Trying to make one explosion do everything was like trying to sculpt a statue with a single hammer blow. What they needed wasn't more force. They needed control. The shift began when a few people started asking a different question. Not how to make explosives converge, but how to shape shockwaves. That distinction mattered. A shockwave is not the same thing as an explosion. An explosion creates the shockwave. But once it exists, that wave follows rules. It travels at a specific speed. It reflects, refracts, and bends depending on what it encounters. Those behaviors were well known in another field: optics. Light behaves differently when it moves through different materials. In air, it travels at one speed. In glass, it slows down. When it crosses the boundary at an angle, it bends. That bending is what makes lenses work. A diverging beam of light can be forced to converge not by changing the light itself, but by shaping the material it passes through. The analogy was uncomfortable at first. Explosives weren't light. Shockwaves weren't rays. But the mathematics didn't care. If a shockwave passed from a fast medium into a slower one at the right angle, it would bend, not metaphorically, physically, and that realization changed everything. Instead of detonating a smooth sphere of identical explosives, what if the weapon used many separate explosive blocks, each carefully shaped, designed to redirect shockwaves inward? Not one explosion, 32. Each one sculpted to do exactly one job. The idea of the explosive lens was born. In theory, it was brilliant. In practice, it was terrifying. Because an explosive lens isn't a lens in the way people imagine glass lenses. It doesn't focus energy gently. It redirects a shockwave traveling faster than a rifle bullet, carrying pressures strong enough to crush steel like clay. To make that work, every detail mattered. The lens had to contain at least 2 different explosives. One fast, one slow. The fast explosive created the initial shockwave. The slow explosive delayed part of that wave just long enough to bend it inward. If the geometry was correct, the shockwave would curve, racing toward a single focal point at the center of the weapon. If the geometry was wrong even slightly, the wave would distort. and distortion meant failure. The mathematics behind this idea were unforgiving. The angles had to be precise. The boundaries had to be smooth. The materials had to behave exactly as predicted. At Los Alamos, mathematicians began modeling shockwave propagation the same way optical physicists modeled light. Equations that once described refraction through glass were adapted to describe detonation fronts moving through explosives. The numbers were staggering. Shockwaves moved at kilometers per second. Timing differences were measured in millionths of a second. Errors smaller than a grain of sand could ruin the entire implosion. On paper, the lens designs began to take shape. But paper was forgiving. Reality was not. The next problem was shape. A single explosive lens wouldn't be enough. To compress a spherical plutonium core evenly, the weapon needed full coverage shockwaves arriving from every direction at the same time. That meant dozens of lenses, arranged into a near-perfect sphere. The geometry that emerged was not arbitrary. 20 hexagonal lenses, 12 pentagonal lenses, 32 total. Together, they formed a pattern resembling a geodesic dome, a mathematical solution that allowed flat surfaces to approximate a sphere with remarkable uniformity. Each lens had to be machined precisely so that it fit perfectly against its neighbors. Gaps were unacceptable. Misalignment was fatal. And each lens was not a single piece. It was two. An outer section made from a fast explosive. An inner section made from a slower one. The interface between them, the boundary where fast met slow, was where the magic happened. That boundary had to be flawless. Any air pocket would scatter the shockwave. Any crack would reflect it. Any contamination would change its speed. Suddenly, implosion wasn't just a physics challenge. It was a manufacturing nightmare. The United States had never produced explosives like this before. Traditional military explosives were designed to be robust, not delicate. They were poured, packed, and handled with the expectation that imperfections wouldn't matter. Here, imperfections mattered more than anything. The project needed explosives that could be melted, poured into molds, and machined like metal without becoming unstable. They needed precise detonation velocities. And they needed them, in large quantities, fast. At the start of the war, none of that infrastructure existed. Factories weren't equipped for this level of precision. Workers weren't trained to handle explosives with tolerances measured in thousandths of an inch. Quality control systems capable of detecting microscopic voids had to be invented on the fly. Even measuring success was a problem. You couldn't test the real lenses repeatedly. They were too dangerous and too expensive. Instead, engineers built surrogate systems using metals, plastics, and diagnostic tools to infer how shock waves behaved inside the real device. High-speed photography captured shock fronts for fractions of a microsecond. X-ray techniques revealed internal deformations. Ingenious timing methods translated mechanical impacts into electrical signals that could be measured. Every test generated data. Most of it revealed new flaws. Shock waves arrived unevenly. Compression lagged on one side. The focal point drifted. Each failure forced a redesign. And each redesign made the system more complex. By now, the explosive lens idea had proven one thing clearly. If it worked, it would work only once. There would be no second chance. That knowledge hung over every decision. Engineers knew they were building something that could not be fully tested in its final form. Every calculation, every mold, every cast had to be right the first time. And there was another layer of risk. Timing. Even with perfect lenses, the entire system depended on simultaneous detonation. 32 separate charges had to fire so closely together that the difference between them was measured in microseconds. Traditional detonators weren't good enough. Their timing variation alone was larger than the entire acceptable window, which meant the radical idea still wasn't complete. Shaping shockwaves was only half the battle. Controlling when they began was just as critical. As the implosion team pushed forward, the project crossed an invisible threshold. They were no longer adapting known technologies. They were inventing an entirely new discipline. Explosives were no longer blunt instruments. They had become components in a precision machine, one that operated faster than human perception and with no tolerance for error. By late 1944, The explosive lens concept had moved from speculation to commitment. There was no fallback plan. Plutonium production was accelerating. The war in Europe was nearing its end. The Pacific War showed no signs of stopping. Everything now rested on whether this radical idea, bending shockwaves like light, could be forced to behave exactly as mathematics demanded. And that meant solving the most unforgiving problem of all: building it. By late 1944, the Manhattan Project had crossed a line it could not retreat from. The explosive lens concept was no longer an idea. It was a commitment. Plutonium production was accelerating. The reactors at Hanford were already delivering material faster than anyone had expected. Every week that passed meant more fissile metal piling up with nowhere to go. The implosion weapon had to work, and it had to work on the first try. That urgency changed everything. Until this point, most of the work had lived on paper and in experimental setups. Calculations could be revised, models could be rebuilt, failed tests could be repeated. Manufacturing offered no such mercy. To build the implosion system, Los Alamos needed to do something no industrial facility had ever done before: mass-produce precision explosives with tolerances tighter than those used in fine machining. This wasn't factory work. It was surgery performed with thousands of pounds of high explosive. The first problem was material. Explosive lenses required at least two distinct detonation speeds: one fast, one slow. Both had to be stable, predictable, and most critically, melt-castable. That last requirement was non-negotiable. Pressed explosives were too inconsistent. Hand-packed charges trapped air. Variations in density would scatter shockwaves and destroy symmetry. The explosives had to be melted into a liquid, poured into molds, and solidified into precise shapes without cracking, separating, or forming voids. In 1944, that ruled out most known explosives. TNT was stable and easy to cast. Militaries had been using it for decades. But it was too slow. Faster explosives existed, but they were temperamental, dangerous to melt, or impossible to manufacture at scale. The solution came from a place few people expected: chemistry, not weapons design. Researchers revisited an explosive known as RDX Research Department explosive. It had been synthesized decades earlier but was considered impractical before the war. RDX was powerful. Its detonation velocity was significantly higher than TNT. In theory, it was perfect for the fast explosive. In practice, it was a nightmare. Producing RDX using existing British methods consumed enormous amounts of nitric acid. It was slow, expensive, and unsuited for large-scale American production. Without a breakthrough in manufacturing, RDX would remain a laboratory curiosity. That breakthrough arrived under immense pressure. Chemists developed a new production method that combined multiple nitration steps into a far more efficient process. The Army brought in industrial partners. Entire factories were built specifically to produce RDX in the quantities the implosion weapon demanded. Time was the enemy. Every delay pushed the project closer to an impossible deadline. Even with RDX available, it couldn't be used alone. Pure RDX was too sensitive. It needed to be blended with TNT and stabilized with small amounts of wax. The result was a new explosive, Composition B, powerful, castable, predictable. It would serve as the fast explosive. The slow explosive presented an even stranger challenge. To bend a shockwave, the slow explosive had to be dramatically slower than TNT, not just slightly slow enough to create the required refraction effect. The answer came from a counterintuitive source: barium nitrate. On its own, barium nitrate barely qualified as an explosive. It was sluggish, almost inert. But when mixed with TNT, it allowed chemists to tune the detonation velocity precisely by adjusting the ratio. After countless experiments, they arrived at a formulation that behaved exactly as the equations demanded. It was slow, it was controllable, and it could be cast. Now, for the first time, the materials existed. That was when the real difficulty began. Each explosive lens weighed over 80 pounds. Each one had to be shaped to tolerances measured in thousandths of an inch. And there were 32 of them. The geometry was unforgiving. 20 hexagons, 12 pentagons, all fitting together into a near-perfect sphere. A single gap no wider than a human hair could ruin the implosion. Air pockets were deadly. Density variations were catastrophic. Surface imperfections were unacceptable. Manufacturing facilities at Los Alamos were transformed. Casting rooms ran around the clock. Steam-jacketed kettles melted explosives at carefully controlled temperatures. Workers poured liquid explosive into precision molds, applying vacuum to pull out trapped gases before the material could solidify. This was not routine labor. Every worker knew that a single mistake could trigger a detonation powerful enough to obliterate the entire building. Yet speed was essential. The explosives had to be cast, cooled, machined, inspected, and assembled again and again while the clock kept ticking. Machining explosives introduced another layer of danger. Unlike metal, explosives could not tolerate friction, sparks, or localized heating. Cutting tools had to be specially designed. Feed rates were slow. Coolants were carefully controlled. Every operation was performed with the understanding that the material being shaped was capable of detonation. Precision came at a cost. Lens after lens failed inspection. Some contained microscopic voids invisible to the naked eye. Others cracked during cooling. Some warped just enough to fall outside acceptable tolerances. Each rejected piece meant lost time and increased pressure. And even a perfectly shaped lens was only half complete. Each lens consisted of two explosive sections, the fast outer layer and the slow inner core. These two parts had to mate flawlessly. The interface between them was the heart of the system. That boundary was where shockwaves bent, where chaos became geometry. Any imperfection at that interface would scatter the wave, introducing asymmetry that no amount of timing correction could fix. Quality control became obsessive. Lenses were weighed, measured, and scanned. Density variations were mapped. Entire pieces were rejected based on deviations smaller than a grain of rice. And yet, even with all this care, there was a problem no inspection method could fully eliminate. You could not see the shockwave. You could not test the real lenses repeatedly. They were too dangerous, too expensive, too time-consuming to replace. Instead, the team relied on indirect diagnostics. They used metal spheres, steel plates, and surrogate materials to observe how shockwaves propagated. High-speed photography captured fleeting distortions. X-ray techniques revealed internal compression patterns. One of the most ingenious methods involved placing radioactive sources at the center of test assemblies. As shockwaves compressed surrounding material, gamma rays were absorbed differently, allowing scientists to infer symmetry from detector readings. Every test added a piece to the puzzle. Every test also revealed new imperfections. The margins were terrifyingly small. At the same time, another problem loomed, one that manufacturing alone could not solve: timing. Even if every lens was perfect, the implosion would fail if the detonations were not synchronized precisely. 32 lenses meant 32 detonation points. If one fired even a few microseconds early or late, the shockwaves would arrive out of phase. Compression would be uneven. The plutonium core would deform instead of collapsing symmetrically. Traditional detonators were useless. Their timing variation was larger than the entire acceptable window. The solution required inventing a new kind of detonator, one that could fire with unprecedented precision. That problem would demand its own breakthrough. But manufacturing could not wait. As winter turned into spring in 1945, pressure mounted across the project. Germany was collapsing, but the war in the Pacific showed no signs of ending. Political expectations were rising. Military planners were waiting. There would be no delay. By April, the final lens assemblies were being completed. Each one represented months of work. Each one carried the weight of an entire war effort. Then, just weeks before the test, inspectors found something terrifying: air pockets. Tiny voids inside several lenses, too small to detect earlier, yet large enough to scatter shockwaves. At that point, the project stood on a knife's edge. There was no time to recast the lenses. No time to rebuild. The only option was manual correction. A chemist knelt on a wooden floor with a dentist's drill, carefully removing material and injecting liquid explosive into microscopic voids working by hand, knowing that a single spark could end everything. This was the reality of engineering the impossible, not a single elegant moment of genius, but thousands of brutal decisions made under relentless pressure. By the time the final assembly was completed, there was no confidence, only commitment. The lenses were as perfect as human beings could make them. Whether that would be enough was about to be tested, and there would be no second attempt. By the spring of 1945, the implosion weapon looked complete. The lenses had been shaped, the materials had been invented, the geometry had been forced into obedience. And yet, the device could still fail for a reason so small it was almost insulting. Time, not minutes, not seconds, microseconds. 32 explosive lenses surrounded the plutonium core. Each one had to fire so close together that the difference between them could not exceed a few millionths of a second. If even one detonated early, its shockwave would arrive too soon and distort the compression. If one detonated late, the shockwave would lag and leave a weak spot. Either way, symmetry would collapse, and without symmetry, there would be no nuclear explosion. The plutonium would squirt outward like toothpaste under uneven pressure, relieving the compression before criticality could be reached. The weapon would fail. Traditional detonators were never designed for this. Military detonators used primer caps, small explosive charges triggered by heat or impact. They were reliable, rugged, and completely unacceptable for implosion. Their timing variation was measured in tens of microseconds. That was an eternity. The implosion system demanded precision tighter than anything conventional explosives had ever achieved. Timing variation had to be reduced by at least an order of magnitude. At first, the problem seemed insurmountable. Explosives were chemical systems. Chemical reactions varied. Even tiny differences in temperature, pressure, or material could change how fast a reaction propagated. Expecting 32 chemical detonators to behave identically felt like wishful thinking. The breakthrough came from an unexpected direction: electricity. Instead of relying on heat or impact to trigger the explosive, the idea was to initiate detonation using an electrical event, something faster, cleaner, and more controllable. That idea led to one of the most counterintuitive inventions of the entire project: the exploding bridge wire detonator. At its heart, the device was deceptively simple. A thin metal wire no thicker than a human hair was placed in direct contact with a small amount of explosive. When a very high-voltage electrical pulse was applied, the wire didn't slowly heat up. It vaporized. Instantly. The metal transitioned from solid to plasma in a fraction of a microsecond. That violent vaporization created a shockwave strong enough to initiate the main explosive charge. The critical advantage wasn't power. It was consistency. Electrical pulses could be controlled far more precisely than chemical reactions. When designed correctly, exploding bridge wire detonators could fire with timing variation measured in less than a microsecond. For the first time, the implosion team had a trigger fast enough and consistent enough to meet their requirements. But the solution introduced a new problem: signal delay. Electricity travels fast, but it does not travel instantaneously. Signals move through wires at a fraction of the speed of light. Over long distances, even small differences in wire length translate into measurable differences in arrival time. In most systems, that didn't matter. Here, it mattered more than anything. If the firing signal reached one detonator before another, even by a few centimeters of wire length, the implosion would be thrown out of sync. The solution was brutally simple. Every wire had to be exactly the same length. Not approximately. Not close enough. Itsob. Exactly. Inside the weapon, the firing cables snaked through the assembly in carefully measured paths. They looped and curved, not because it looked elegant, but because every path had to match every other one down to the smallest detail. Engineers measured not just the copper wire itself, but the insulation surrounding it. Different materials altered signal propagation speed. Thickness mattered. Bends mattered. Nothing was left to chance. Each explosive lens received not one detonator, but two. Redundancy was non-negotiable. If one detonator failed, the backup would fire. If both failed, the lens would not detonate, and the entire implosion would fail. There were 64 detonators in total. All of them had to fire correctly. All of them had to fire together. Testing the detonators was its own ordeal. Individual units were fired repeatedly to measure timing variation. Circuits were refined. Power supplies were redesigned. Every improvement shaved fractions of a microsecond off the spread. The acceptable window was merciless. Too wide, and the implosion would distort. Too narrow, and the system would become too fragile to trust. By now, the implosion weapon had become a machine that operated faster than human perception. No one involved could directly observe what mattered most. Everything depended on measurements, instruments, and trust in mathematics. The pressure was relentless. There was no way to fully test the complete system. Detonating the full array even once would destroy the weapon. There would be no second run, no data to refine. The only thing the team could do was test components in isolation and hope that the assembled whole behaved exactly as predicted. As the Trinity test approached, anxiety spread through the project. The explosive lenses were perfect on paper. The detonators were fast on paper. The wiring was matched on paper. But the margin for error was zero. A single microsecond could separate success from failure. In the final days, every subsystem was rechecked. Wires were remeasured. Connections were inspected. Power supplies were verified. No one spoke casually anymore. This wasn't fear of death, although that was present. It was fear of anticlimax. After years of work, after inventing entire fields of science and engineering, the weapon could still fail silently, reduced to a costly explosion that accomplished nothing. That possibility haunted everyone involved. The implosion weapon had demanded perfection at every level. Geometry, chemistry, manufacturing, and now timing. Each problem had been solved, just barely enough to move forward. Timing was the last barrier. If it failed, everything failed with it. And there would be no opportunity to correct the mistake. When the final system was assembled, it was no longer a bomb in the conventional sense. It was a synchronized event. 32 shockwaves, created separately, racing inward at unimaginable speed, converging on a single point in space within a window of time shorter than a blink, shorter than a nerve impulse, shorter than human awareness. Whether that convergence would happen as designed was no longer a question science could answer. Only reality could. By July 1945, there was nothing left to adjust. The equations had been solved. The materials had been cast. The lenses had been machined, corrected, and assembled. The detonators had been tested to the limits of measurement. Everything that could be controlled had been controlled. What remained was faith. In the early hours of July 16th, a violent thunderstorm rolled across the New Mexico desert. Rain lashed the ground. Lightning cut across the sky. The test was delayed not because of fear, but because even the weather had become a variable that could not be ignored. At base camp, scientists waited in silence. This was not the atmosphere of celebration often imagined later. There were no cheers, no speeches, only tension. The device stood alone atop a steel tower in the desert. Inside it, 32 explosive lenses surrounded a small sphere of plutonium, barely larger than an orange. Years of work had been reduced to a single question. Would 32 separate detonations become one event? At 5:29 a.m., the countdown reached 0. 64 exploding bridge wire detonators fired. Not one after another, not in sequence. Together, within a few millionths of a second, the explosive lenses did exactly what they had been designed to do. Shockwaves raced inward, bent by carefully shaped boundaries, converging toward the center of the device. The plutonium core compressed violently. Density doubled in less than a microsecond. At that moment, physics took over. The core went supercritical. Neutrons multiplied faster than they could escape. In the time it takes a human nerve to fire once, tens of generations of fission occurred. A flash brighter than the desert sun lit the horizon. Observers miles away felt heat on their faces. Some instinctively turned away, even through darkened goggles. Then, after a long pause that felt unreal, the shockwave arrived. The sound rolled across the desert like distant thunder, followed by a pressure wave strong enough to knock people backward. Above it all, a massive cloud climbed into the sky, rising mile after mile, carrying dust, steel, and the remnants of a tower that no longer existed. The implosion had worked, not approximately, not partially, perfectly. For George Kistiakowsky, the man who had spent months forcing explosives into obedience, the moment carried a private weight. He had bet his own money that the explosive system would function. He had been right. But celebration was brief. Everyone present understood what this success meant. The test proved that implosion was not a gamble, it was a reliable method. The same design would be used again, without alteration. 3 weeks later, an identical device detonated over Nagasaki. World War II ended soon after. Yet for many of the engineers and scientists involved, the deeper realization was not about destruction. It was about precision. Explosives, once the crudest tools of war, had been transformed into instruments capable of microscopic control. Forces that once spread chaos had been bent, shaped, and synchronized with extraordinary accuracy. The Trinity test marked more than the birth of the atomic age. It marked the moment engineering proved it could force even the most violent processes in nature to obey. Just long enough to change the world. The Trinity gadget worked only once in the desert that morning, but its influence never stopped spreading. 3 weeks later, a weapon built on the same implosion design detonated over Nagasaki. The war ended soon after. History moved on. Yet the most enduring legacy of the Trinity gadget had little to do with nuclear explosions. It changed how engineers thought about control. Before 1945, explosives were blunt instruments. They were judged by power, by yield, by how much they could destroy. Precision was not part of the conversation. The implosion system shattered that assumption. For the first time, explosives were treated as components in a machine shaped, timed, and synchronized with extraordinary accuracy. Shockwaves became predictable. Chaos became calculable. That shift quietly gave birth to an entirely new field: detonation physics. The techniques developed under wartime pressure modeling shockwave propagation, controlling material interfaces, measuring events that occurred faster than human perception did not disappear when the war ended. They spread. Shaped charges, first refined for the implosion lenses, became essential tools in modern engineering. In oil and gas drilling, radial arrays of shaped charges are used to punch precise channels through rock, creating controlled pathways for resources to flow. In mining, controlled blasting techniques allow engineers to fracture material without collapsing entire structures. In modern spacecraft, linear-shaped charges are used to separate rocket stages, cleanly and reliably cutting metal at exactly the right moment, with no room for error. Even today, advanced explosives manufacturing still relies on processes first developed for the Manhattan Project. Factories built under wartime urgency continue to produce specialized explosives using methods refined in the 1,940 seconds. But the most important legacy was not technological. It was conceptual. The implosion weapon proved that complexity could be mastered not by brute force, but by understanding. Every major obstacle the project faced seemed insurmountable at first. Explosives refused to converge. Materials did not exist. Manufacturing tolerances seemed impossible. Timing demanded precision beyond measurement. Each problem was solved not by a single breakthrough, but by breaking assumptions. What if explosives didn't have to behave the way they always had? What if waves could be shaped? What if precision mattered more than power? Those questions changed everything. They are the same questions that continue to drive engineering today. Whether the challenge is controlling nuclear reactions, designing microprocessors, or guiding spacecraft millions of miles from Earth, progress comes from forcing complex systems to obey rules that once seemed out of reach. The Trinity gadget's 32 explosive lenses surrounded just 6 kilograms of plutonium, but they represented something far larger. They marked the moment humanity learned that even the most violent forces in nature could be shaped briefly, precisely, and deliberately. Not because they were weak, but because understanding had become stronger. If you found this story compelling, there are many more like it hidden beneath the surface of familiar events. Stories where small decisions, obscure engineering problems, and forgotten innovations quietly shaped history. In the next episode, we'll explore another moment when ingenuity changed the course of the war not through firepower, but through code, machines, and mathematics. If you want to continue exploring the technical side of history, consider subscribing. And if this video changed the way you think about engineering, precision, or control, let us know in the comments. Because the most important stories aren't always about what happened, they're about how it became possible.